Hi, welcome to Key Features of the F# language. In this section of videos, we'll review some key features of the F# language that we'll use throughout this course. I'm assuming you've already seen these language features before, so I won't go into depth about the syntax. But I do want to make sure you understand why these aspects of the language are so useful in functional programming. Here's what this section covers. In this video, we'll review the basic immutable data structures you can use to model your problem domain. The second video will review the basic types of collections that can model groups of objects. The next video looks at how to use functions as objects, which is the heart of functional programming. In the fourth, we'll see how to leverage F#'s built-in libraries of collection functions to implement complex algorithms with very little code. In the final video, we'll tackle how to make your functional F# solutions interoperate with software written in other languages like C#. After reviewing these basic features of the F# language, you'll be ready to learn powerful ways to apply them in the rest of this course. Welcome to Domain Modeling with Immutable Data Types. In this video, I'm going to show useful ways you can model the problem domain with the four main kinds of immutable data types in F#: tuples, records, discriminated unions, and options. We'll discuss the advantages of using immutable data types in general and the special advantages of each type. In functional programming, a type is anything you can pass into or get back from a function. We use immutable types to model the data in the real world, while functions model the behavior. The most important characteristic of the immutable data types is that they are immutable. But another great thing about them is that they use value-based comparison by default. That means that whenever F# needs to decide whether two immutable data type instances are equal, or if one is greater or less than another, F# compares the values they hold, instead of checking if they have the same location in memory. A third important point is that immutable types must always be complete. When you create an instance of one of these types, you must always provide a value for each of its members. And whenever an instance of that type appears, you will know that it won't be missing any of its members. Let's see all this in action. The tuple is the simplest and most flexible of the immutable data types. With a tuple, you can bundle together any finite, ordered set of values. And each of these values can be of any type. One of the most common uses for tuples is to define a set of values that must be passed together into a function. It's also a convenient way to make a function return more than one thing. So here in this function, I'll pass in a tuple of integers and return another tuple calculated from the inputs. A tuple doesn't assign names to its members. When you declare a tuple as part of a function signature, you give its members names in the parameter declaration. But you can also do this anytime, as I'm going to do right here. So I've said that x is going to have the value of the first member of the tuple, and y will have the value of the second member. Now, remember I said immutable data types support equality and comparisons based on their values. That's easy to illustrate with tuples. Even though these two tuples were declared separately, because their values are equal, F# says they're equal. And here, the first of the two values are the same, but the second two are not, and so F# says the first one is less than the second. One drawback of tuples prior to F# 4.1 is that they had to be reference objects. In .NET, a reference object is allocated in heap memory and gets cleaned up by the garbage collector. This can slow down a program if you have a lot of tuples. In F# 4.1, tuples are still reference objects by default, but we can choose to make them value objects by using the struct keyword. A value object is allocated on the call stack instead of the heap, and it's cleaned up immediately when all references to it go out of scope. You probably won't see much difference in performance using the struct keyword in your F# interactive testing, but in the real world, if there are a lot of tuples being created, the performance improvement can be significant. Records, like tuples, let us bundle together a finite set of values. But unlike tuples, each record type must have an explicit name, and so must each of its members. Records are the immutable data type that's the most similar to plain old classes in object-oriented programming. The syntax for instantiating a record is very similar to the similar syntax for a class or struct in C#. If the names of the members are unique in the current scope, then F# can infer what type of a record you're using based on just the member names. So here I'm going to write a function that's going to take a record as a parameter. Notice I haven't specified what type the parameter is. I'm going to make it return a tuple composed of members of the record. And as soon as I specify the first name element there, F# figures out that I must be talking about a person record, since there's no other type in scope that has a first name member. Like tuples, a record is a .NET reference type by default. But in F# 4.1, you can give records an attribute called struct, and that will make them behave as value objects, just as tuples will. Again, you're not likely to see much performance difference in F# Interactive, but in the real world, this could be significant. A very powerful kind of immutable data type is the discriminated union, which some people like to call choices. There's really nothing like them in C#. At the simplest, a discriminated union is just a set of names, in which case it can be used much like an enum. But the real power of discriminated unions is that each case can have any kind of data associated with it, and the kinds of data for each case don't need to be the same. Here's an example you might remember from when you learned object-oriented programming, the shape type. It's perfectly fine that the kind of data we need to represent each case is different. Discriminated unions are a good choice when we want to model different kinds of things that can all play a common role, such as shapes in a graphics program. They're also good for modeling the states that an object can pass through, such as in this example. Notice that in this case, I gave a name or a label to each of the data points within the case. Up here I just left them anonymous. The final kind of immutable data type we'll use in this course is the option, which is a special kind of discriminated union. We use options when we anticipate that there might be a value, but then again there might not. Functions and logical expressions often return options to indicate when they have nothing to return, without having to throw an exception or return null. So for instance, this function checks to see if it might be dividing by 0, and returns none in that case instead of making an exception or returning a null or a default value. Otherwise, it returns some with the result.